Okay, the next section in optimization is called neural networks. So I want to show here a graph of a neural network being trained on some data. And the question is, speaking of gradient descent, does this graph remind you of a topomap or how you would use a topomap? Certainly it does to me. It's got that sort of descent through the different contours in the map. And that's really what you're doing when you're training a neural network. So I wanted to drill down into this and show how do neural networks function, how do we train them. Typically we're talking about multiple layers of artificial neurons. So you've got some input, maybe you've got a bit vector for some input, an image that you're presenting to the network to train it. And then you've got some different layers, we call them hidden layers in most cases. And then you've got some expected output, what you want to train for. So you present your input and your expected output to the input and output layers respectively, and then you let the neural network just churn on that, propagating weights through the network until it finally drops down into an energy state where it can recognize the input and give you the right output. Okay, so that's one pattern. Now let's throw in some more. Let's throw in another input pattern that's different with a different expected output, on and on and on. And you keep adjusting the weights and making sure that you try to come up with a good representation of what the expected output is. In the case of Google's use of deep learning, again, there's some pretty good videos on this, but they're talking about having 10 layers of neurons stacked up, where the very bottommost might be looking at patterns inside of images, just little high contrast edges or shapes, but then they build up higher and higher into different levels of increasingly conceptual representation of what you're trying to recognize. So you might just be looking at the bits way down here and the edges in an image, but then at a higher level, maybe you're recognizing a frog or a fly or something. And it can be used for text, image, sound, etc. So our sample company, foodbartender.io, has cut a deal with several large municipal governments, and they really want to avoid delivering alcoholic drinks during parades. For some reason, it just makes the crowd too lively. So the cities pushed back on this, and they told Food Bartender, hey, you can operate here, you can fly your drones in our urban areas, but not during parades, okay? And the problem with parades is it's kind of hard to tell where the parade really is, right, unless you're tracking it. So the city vehicles have installed special beacons for that. So they can track where the parade route is at any point in time, and they just want to make sure that the drones aren't delivering drinks right there. So the problem stated is to train a classifier to recognize the beacon signals shown in the table below for parade route avoidance. Okay, so we've got this policy that we're going to set up for how we fly the drones, and it's okay to do a delivery if you're catching beacon signals off the city vehicles that say 000 or 010. But if the beacons are coming up with 100 or 110, then that means you've got some state of a parade in progress, and you want to avoid those areas. So we're going to have to set up some classifiers on the drones so they can recognize these signals off the beacons. Now, the following example requires some additional software. NeuralLab is a pretty nice package showing how to do a number of different types of flavors of neural networks. Recurrent networks, etc. If you want to get into some deep learning, if you go through the instructions there, it'll show you how to install that. If you want, it's a Python interface, but you'll have to do some additional installation on that. If you have easy install or pip or one of those, it makes it a lot simpler. Okay, so I've got some code here for a neural network. Let me drop into Python for that. Okay, I've got some Python here for implementing neural net and testing it out. It's cut and paste here. First we import NumPy and also import NeuralLab that we were talking about. So cut and paste that. All right, so I'm creating a neural network there. And it's got two inputs, 4 neurons in the hidden layer and 1 neuron in the output layer. So it's basically going to be a binary output. All right. And next up, I'm going to train this. So if you notice, I've got train_GDX. It's using a gradient descent to train it. And so I'll go through here, it'll go through all the different epochs, all the different iterations on gradient descent until it's got that whole network trained to recognize particular inputs and give the required outputs, basically going to a lower energy state. Blam! Okay, great. So we go through 190 epochs, and we get our error reduces by, it looks like about 15x. So now we've got a neural network that we can test. So let's try this out. I'm going to throw a few different patterns in there and see if it's got the expected results. And what will come back is it'll be numbers that are close to 0 or 1. We'll probably have to round those just to get to the actual numbers. Blam. Okay, so the first one is I'm going to throw in the pattern of 0, 1, 0, and I expect a 0 coming out. And yeah, great, I got 0.04. If we round that, we get 0. Next one is 0, 0, 0. Again, if we round that, we get 0.029. So we round that, we get 0. And then third pattern, I throw in 1, 1, 0 as my inputs. I expect to get a 1 out. I get 0.95. If I round that, it goes to 1. And last one is input pattern of 1, 0, 0 for the beacon signal. And I expect to get a 1, and I get 0.89. Round that up to 1. Great, that worked out. Okay, so we've built this neural network as a kind of classifier for parade avoidance to make sure that keep City Hall happy. And we've got 3 inputs, 0s and 1s for our beacon signal. We've got this hidden layer in between of neurons where the weights are being adjusted to do the recognition. And then we've got a binary output, 1 neuron there. And this trained, actually, the time that I ran it before, it trained in 150 epochs. I think this time it trained in 190, but roughly the same order of magnitude, 150, 200, somewhere around there. As a sidebar, I'd like to focus on somebody who really kind of founded this field back in the day. His name is Norbert Wiener, and he's credited with really establishing cybernetics. I mean, certainly the term comes from earlier usages dating back to the Greeks. Obviously, it's kind of a portmanteau off of some classical Greek works. But what Norbert Wiener did was he was focusing on how to build filters, how to adapt to noisy signals. So basically, you've got some kind of input, and you've got some kind of filter classifier, if you will, and you want to be able to use some feedback loops to adjust the filter, automatically tuning it to adapt to changes in the input. This was applied during World War II. Actually, he was doing work on cybernetics back in the 1920s. But then, rolling the clock up into World War II, they had radar, but the radar was separate from, say, like the anti-aircraft weapons they were using in the Battle of Britain. So what Norbert Wiener did was to connect the two together and have a kind of control system for where you could take the input signals off the radar and then use that for targeting the anti-aircraft guns. And so these kinds of control systems, the theory behind it, we talk about first-order cybernetics. And later work by Norbert Wiener is very interesting. He really started focusing more and more on this idea of having a lot of people and a lot of machines at large scale cooperating, if you will, which gets back to our notions of workflows, data workflows. And actually, if you read Norbert Wiener, he got into more and more social issues and the ethics of automation, really. There's some great books of human use of human beings, other titles that explore different ethical issues. He starts talking about a kind of day when there's a whole bunch of machines that people are using to get information. It sounds a lot like people doing Google queries, really. It's kind of fun to think that this was done 50 years earlier or so. And there's an ascendancy there. If you look at some of the computer scientists who were very heavily influenced by Norbert Wiener, you'll find that one of them happens to have been a name on the Google patent for PageRank, Larry Page's advisor back at Stanford. So, I think that Norbert Wiener really set the stage and really envisioned a lot, like I say, going back to the 1920s, kind of at the same time that Alonzo Church and Haskell Curry were doing their work on lambda calculus. Another thing that Wiener did that was very, very substantial was, even though he was working in signal processing, electronics, control theory, he recognized a need to branch out and leverage certain aspects of biology. So he recruited two biologists to come to MIT, where he was at, recruited these two biologists to come to do research at MIT on pattern recognition, namely McCullough and Pitts. So McCullough and Pitts, I recommend an excellent paper about their work. Jerome Letvin was somebody else on their team who wrote a summary of what they'd done later on, years later, entitled "What the Frog's Eye Tells the Frog's Brain." So these two biologists came to MIT and they started studying what are the signals that come across from a frog's eye across the optic nerve back to the frog's brain, so that the frog can track a fly moving around in front of it and be able to capture it. You know, oddly enough, this is a lot like what Norbert Wiener was doing during Battle of Britain, to take radar signals and use those to steer the anti-aircraft weapons. So it's kind of interesting. He was able to cross over from signal processing into biology. And then McCullough and Pitts became, you know, one of the real first leading teams in this emerging field of neural networks. There had been notions of neural networks before, perceptron and whatnot, but they weren't quite as well biologically inspired. They were much more abstracted. So McCullough and Pitts really came out with, in my opinion, what's one of the first biologically inspired neural networks. And their idea was that you could define artificial neurons and use them to train features, recognize patterns and signals, and that, you know, this would be really good at adapting to having noisy input or partial input. So you can think about that. You could train up a neural network on, say, an image, and, you know, present it with a number of different images. There's an image of a cat, an image of a dog, and things like this. Now, if you come back in with the same images, but maybe, you know, parts of those images have been corrupted. So, you know, the cat's missing its left ear in the image. The thing about the neural networks is that they can recall the full image. They can reconstruct what they'd learned before. So they're very good at working with partial input or noisy input. So if you get into things like image recognition, speech recognition, different kinds of text can be transformed into this, then neural networks turn out to be pretty interesting. I spent about 7 years doing neural network research and development back in the 90s. And you know, it was fun in the early days of IJCNN. It's even more fun now, many years later, to see things like deep learning being used at scale at places like Google, where, you know, the ideas that we were struggling with having enough computation for back then are coming out to being big commercial successes now. So anyway, I definitely recommend this paper. It's an entertaining read. And there you've got, I think, Letvin and McCullough holding a frog.